Welcome to the WION podcast, where we explore fascinating stories and ideas from various fields. In this episode, we explore how a single heavy particle can bridge two opposing quantum realities, revealing how hidden motion reshapes matter, unifies rival theories, and transforms our understanding of complex quantum systems. Scientists at the Institute for Theoretical Physics at Heidelberg University have discovered a hypothesis indicating two major perspectives in modern quantum physics, focusing on how a single, unusual particle acts inside a multi-level body system filled with fermions, referred to as a Fermi sea. This new hypothesis describes how quasi-particles come to light, connecting two quantum states that were earlier considered as separate. Following the discovery, the Heidelberg team confirmed that this unified approach will lead current experiments in quantum matter. Physicists have earlier debated about exotic electrons or atoms interacting with large numbers of surrounding particles. In terms of the quasi-particle model, a single particle travels through a sea of fermions, which include electrons, protons, or neutrons, and interacts persistently with its neighbors, according to a report in the SciTech Daily. When the particles travel, they attract neighboring particles surrounded with it, forming an entity identified as a Fermi polaron. In fact, it reflects the coordinated motion of the impurity and the particles near it. A doctoral candidate at Heidelberg University's Institute for Theoretical Physics, Eugen Deiser, explained that this idea has become vital for strongly interacting systems that range from ultra-cold atomic gases to solid materials and even nuclear matter. A contrasting scenario is the so-called Anderson orthogonality catastrophe, which arises when an impurity is so massive that it effectively becomes stationary. The mere presence of such an impurity drastically reshapes the many-body system, causing the surrounding fermions' wave functions to change entirely. Their original structure breaks down, leading to a complex background that disrupts collective motion and suppresses the formation of quasi-particles. For many years, physicists lacked a unified theory capable of connecting this static limit with models describing mobile quasi-particles. Using a combination of analytical methods, researchers in Heidelberg have now succeeded in unifying these two pictures within a single theoretical framework. The theoretical framework we developed explains how quasi-particles emerge in systems with an extremely heavy impurity, connecting two paradigms that have long been treated separately, said Eugen Deiser, a member of the quantum matter theory group led by Professor Dr. Richard Schmidt. One of the key insights of the new theory is that even extremely heavy impurities are never completely immobile. As the surrounding medium reorganizes itself, these particles experience minute motions. These subtle shifts open an energy gap that makes quasi-particle formation possible, even in a strongly correlated and complex environment. The study further shows that this mechanism naturally explains the transition from polaron-like quantum states to molecular quantum states. Thanks for tuning into this incredible story. If this episode resonated with you, don't forget to hit the like and subscribe button for more captivating stories to come. Stay tuned.